Now we are building upon our simple generalization of standard Hooke's law to the generalized setting, and ultimately we're demonstrating step by step its usefulness and in fact necessity. And here is a nice example where it's simultaneously useful and necessary, and the example is going to help us also analyze a structural scenario of practical interest, namely pressure vessels. And we are going to, in particular, consider a cylindrical pressure vessel. So a pressure vessel ultimately is anything that contains a gas, or let's say gas in liquid form, ultimately to keep it in liquid form, in order to transport it from one location to another. It could be a gas canister, and it could be essentially a vessel that's being carried by a truck from one location to another, and it could be an aerosol can. It could even be a simple soda can, which is actually pressurized to a certain extent, right? And so in all of these cases, the analysis of a cylindrical pressure vessel is eventually of interest. And so we're going to look at a simple scenario, one simple scenario, in which the pressure vessel has a cylindrical form. Now you might notice that pressure vessels come not in many different shapes. There are different dimensions to it, but they are often either cylindrical or spherical. And in fact, you can remember from various maybe documentaries or observations that vessels that are subjected to extreme pressures are often of spherical shape. And in this, like a submersible that goes deep into the ocean is of spherical shapes. In this example, we're going to see why that is the case. And let me add here a keyword that's going to become relevant soon. Our pressure vessels will be called thin-walled, and we'll explain it in a minute. What exactly that refers to. So the pressure vessel is essentially in this case it's a cylinder, and we are going to look at a pressure vessel with closed ends. And these closed ends ultimately, here I'm drawing them arbitrarily, but they will be of a hemispherical shape. Okay, so that's a vessel with closed ends. All right. That could be put at the back of a truck, and it could be carrying a gas at a certain pressure, and in order to be able to carry that gas, this thing needs to have a certain amount of carrying capacity. Inside should be empty, and you put the gas inside and then transport it, right? So that's the kind of structure that we want to analyze. And now I'm going to draw this vessel without depicting the ends explicitly first. So and let's try to do that in 3D to the extent that's possible. So this is the cross section. If you like, I'm cutting off here, or for that matter, I'm looking at any intermediate portion, really not that important at this stage. And so that is our vessel, right? So that's just the intermediate cylindrical portion. And it's going to be made of a certain material, say steel, and it will have a certain wall thickness. That wall thickness, let us call it T. And also, it is going to have a certain radius. Now, that radius is going to be the distance from the center line to the solid portion of the cylinder. Now, the distance from the inside to which point? To the inside, to the outside, somewhere in the middle. In practice, it will matter. But because we're making the assumption of a thin wall, I will often just denote a single radius value. R could be to the inner wall, to the outer wall, or to some point in between. For our practical analysis purposes, it will not make a difference. The difference in the values that you can alternatively take, like the inner radius, outer radius, etc., will all differ by values that are associated with this wall thickness. And thin-walled means that T is much, much less than R. Okay. Now, as soon as you see a much, much less than R, or in other words, if I see that T over R ratio is much, much less than 1, the first question you can, of course, naturally ask is, well, how small is small? So in other words, T over R ideally should be going towards 0. It's not 0, but very, very small. But what is small? Is 1 over 100 small or 1 over 10 small? So in that case, our reference point is essentially a value that we can compare it against. So, and the value we can compare it against is going to come from, not from our analysis, but ultimately the guide comes from an analysis that is not going to invoke this assumption. So, there is a theory, a mathematical approach to such problems involving linear elasticity, with which you can go ahead and solve for the stresses that are induced in a pressure vessel. So soon we will put a pressurized gas inside and we'll look at the stresses forming. And we can calculate the stress field exactly without invoking this assumption. Then we invoke this assumption, and we invoke it because it greatly simplifies our life. And we're going to solve the same problem again without requiring all of that mathematical detail. We're just going to be able to do it the way we do it now in a few minutes, and come up with approximate answers. And then we compare those approximate answers with the exact elasticity solution, the mathematical solution. And then we compare how close they are. If they are close enough, then I deem my approximate analysis to be good enough. Okay? And now the question is, how close would you like those stresses to be? Now, there is no absolute answer to that question, but what I can tell you at this stage is that if T over R, in practice, if it is roughly less than 1 over 10, then thin-walled assumption is an assumption that will more or less check for us. If T over R ratio is larger than 0.1, then the error you're making in the calculation of the stresses with this assumption starts to become significant, and you better not make use of that assumption. If the ratio is even smaller, then you're even safer. Your assumption will work even better. Okay, so that's the value that we're going to compare against presently. So we don't know the values of T and R, so we're going to check that in a second. So in your book, by the way, and in the appendix, eventually you will find expressions for the exact stress distributions that do not make use of the thin-walled assumption. That's called the thick-walled cylindrical vessel. You can look at those expressions and appreciate the complexity that you're facing. Whereas in this case, it's going to be much easier. Okay, so now we're going to analyze a problem that has a cylindrical geometry, and it will be useful, it turns out, to attach a coordinate system that is essentially going to reflect that cylindrical geometry. So in this case, a cylindrical coordinate system. We're going to call the axial direction x. It really doesn't matter if we call it x, y, or z. It's just in this case, I'm going to pick x, sort of suggestive of x, the axial direction. So this is the axial, or sometimes called the longitudinal direction. Good. So, right, so we're in 3D, so I want to have 3 coordinate directions which are perpendicular to each other. Instead of x, y, z, we're picking 3 directions that are suiting the geometry of this problem. The second direction, obviously, is a direction that moves around the circumference of this tube. So that would be a direction that goes like that, okay? So that direction which moves around the circumference is going to be called the circumferential, or the tangential, or the hoop direction. So there are several names to it, and it's customary to denote it either by theta, because that's the direction that you usually indicate that that direction with in cylindrical coordinate system, but we will also call it t, not to confuse it with the thickness, by the way, right? So has multiple names, theta or t. In fact, I will prefer t when eventually I write the stresses, because the stresses are called the direction is called the tangential or circumferential or the hoop direction. They are all the same thing. And now one direction, so if I look at this thing along the axis of the cylinder, the picture I will see, or if I look along that direction essentially, right, along the x direction, the picture I'm going to see is simply a disc, a very thin walled disc, okay? And what we're saying now is that if I move in, that's the x direction, okay? And along that direction, that is the tangential or the hoop direction. Okay, so that's x, the blue direction. And now there is a third direction, which has to do with the radial direction, okay? So radiuses are, I'm denoting the radial direction also hopefully without causing confusion. And that's the direction that's like a right-handed coordinate system. X cross t or theta is gonna give the outwards direction. That's the radial direction r. Okay, so instead of having x, y, z, we will have x, t, r. We don't have to call it x, we can call it y. In fact, I don't have to call these x, t, r. I can call them 1, 2, 3, a, b, c. It doesn't matter. What matters is not what we exactly call things. It is important what we call them for the purposes of effective communication, but for ultimate calculation, I just need to understand what it is that I'm trying to refer to. So that's the notation that I'm going to use in the context of this example. Okay, so now that we have some information about the geometry, let me also give a length to this piece of the vessel that I am analyzing. L could be it could be just the cylindrical portion's length in this picture, or for that matter, any length that I'm going to cut away from that cylinder, the vessel. And I'm going to try to go ahead and analyze the pressures, the stresses that eventually form in this structure due to the fact that in this vessel there is a pressure that is applied onto the surfaces, right? So the pressure applies normal to the surface. That's the meaning of a pressure at every point, okay? And that pressure is going to be indicated with P. Okay, so let's write it over here. And in this problem, we know that P is equal to 2 MPa, and we know that it is internally pressurized. Okay, so that's the pressure on the inside. Now, I will carry out an analysis, and ultimately, we could actually have the following scenario. Well, what does it mean that it's internally pressurized and that internal pressure is 2 MPa? Well, on the outside, there's probably an atmosphere as well, and that atmosphere will also have its own pressure. So when we say P, really what we are referring to is P equals, the P that goes into our equations is actually the physical internal pressure minus the physical external or outside pressure, okay? So if the internal pressure is larger than the external outside pressure, outer pressure, then the difference, P, is positive, it's 2 MPa, and we call it internally pressurized. If the internal pressure is less than the outer pressure, then the P, the difference, would be negative, and we would call it either minus 2, let's say, internally pressurized. That would be strange. Instead, we would say P equals 2 MPa externally pressurized, in which case it would stand for PO minus PI instead of that minus that, right? So ultimately, this P value that we are writing here indicates essentially the difference between the inner and the outer pressures. Now, having said that, the subsequent analysis is just going to assume that it's internal. If it turns out that it's a negative value, so 2 MPa plus external pressurized, you're just going to put a negative value for P in there that reflects that difference, and the whole analysis remains the same. Now, whether it's positive or negative will influence whether the stresses are tensile or compressive, but again, that will come through the sign. Okay, so now that's the internal pressure. 2 MPa, no big deal. 2 MPa we can understand and appreciate that it's a relatively small stress. But let's see and calculate these stresses themselves that is associated or induced within the thin structure and see actually if they are small or not. So then I need to give you some information about the geometry. The thickness is equal to 5 millimeters. The radius, which radius doesn't matter, 1.5 meters. Why does it not matter? Because I can look at the ratio of T to R and I can see that that ratio is actually 1/300. And that certainly is much less than 1, even smaller than 0.1. So I'm certainly safe with respect to the assumption of a thin wall structure. So the approximate stress analysis that I will be doing is going to be actually quite accurate. Accurate with respect to what? With respect to the exact analysis of stresses that we cannot do in the context of this course. So finally, I need the value of the of this length, if you like, that I can take. We will not directly need it, but let's just write it if that is comforting for you. Turns out it's not going to appear in any of the results until I come to the very end. So for the purposes of stress derivation, this length is not important, but we are going to be eventually concerned with the elongation of this cylindrical pressure vessel due to the action of the pressure, and then we will refer our strain with respect to a relative dimension, and that's going to be this length of L. Okay, so therefore it might be useful to imagine this L to be the length of the cylinder that we have. Okay, good. So finally, we need material properties. In this case, it's steel, so we can imagine quickly that the Young's modulus is 200 GPa and the Poisson ratio is 0.3. And the question is very simple. Find, due to the action of the pressure after the cylinder is pressurized, find the change in the length, the change in the radius, and the change in the thickness of the cylinder. Okay, so that's the question. We're now going to attack that question based on the important assumption of a thin-walled vessel plus the fact that we just called it closed ends. Right? So let us go ahead and now attack this problem. And the first thing I'm going to try to do is I am going to try and calculate the stresses that are associated with this coordinate system. So first of all, irrespective of the type of coordinate system you use, Hooke's law will always hold. So in other words, there will be normal strains and normal stresses associated with three directions. Those three directions could be standard X, Y, Z, or for that matter, any other system. X, T, R, A, B, C, even a spherical coordinate system would eventually give rise to a stress-strain relation that's expressed in exactly the same manner. So therefore, just like I am going to expect normal strains associated with each direction, I'm going to also expect normal stresses associated with each direction. So in other words, the first step, let's think conceptually. To find changes in dimensions, I need to know the strains. To know the strains, I need to calculate the stresses, and therefore, I need to relate the stresses to the type of loading. So here we are going to go through the whole loop of load to stress to strain to dimension change or deformation. That's our solution line. Okay, so material behavior is reflected here. Static equilibrium analysis is reflected here. Okay. Equilibrium, and here we will use the definition of strain, some simple math. Okay. And here comes eventually, ultimately, linear elasticity. Assumption on the material behavior. Okay. So the first step we need to take is calculate the stresses from equilibrium. Now, we're only going to be concerned with normal stresses and strains because in this problem, there is no shear inducing forces. So if I had taken this pressure vessel looking like this, and if I had tried to torque it, and in the future we're going to look at problems where we have such loading, then you would additionally have shear stresses. And in some of the examples eventually that you'll consider in the homework, you will have shear stresses. But presently, it turns out we will have only normal stresses and hence normal strains, and these quantities, changes in the length, are associated with actually normal stresses. So the first thing that I will do is I will go ahead and take a cut along the direction. Let's do it with red here. Along the axis of this cylinder, like this. Okay. So I'm gonna take a cut, okay, a knife, and just slice through this pipe, okay, this vessel, and I'm going to try to draw what I see as a result of that. So the first step in my solution, and this is the depiction of what I see. So this red surface is where I sliced through the pressure vessel, and I've drawn the free body diagram of the whole thing. Okay. So that's the free body diagram of the left side. And now I remember that this thing is internally pressurized. Okay. And this pressure will eventually induce a net force along that direction. Now, that direction, locally, I want to embed a coordinate system. So that direction, the axial direction is certainly x. There's no doubt about that, right? So that is the x direction, the axial direction. The other direction, let us call that the y direction. Okay, for the purposes of analysis, that's the direction that is here, going in that direction. That's normal to the red plane. And so pressure induces a net force along the y direction, and what holds the material together to resist that force is stresses or forces building up on the red surfaces where I took a cut, right? So those are going to be internally generated forces or stresses as a reaction to that pressure, and they have to have opposing direction, and that direction indicates that they are along the direction y, okay, on the plane with normal y in the y direction. So these are normal stresses that are generated on that surface. So locally, my coordinate system is directed along the y direction, but notice that if I take any other cut, so for that matter, presently the cut I've taken when I look along the x-axis, if I take that view, my cut is looking like this. Okay, so pressure pushes in that direction, sigma is normal stress is acting in that direction. Well, I could have taken a cut, sliced it at another angle. Then, in that case, I would have observed a cut that's like this. Then the normal stresses opposing the net force due to the pressure would be situated in that direction, and so on, every time the direction of the opposing normal stresses is along the hoop direction, along the circumferential or tangential direction. So the stresses that are forming, I'm going to call them in general sigma t or theta. So presently I've indicated that direction to be y, but in general that would be really a tangential direction. Okay, so sigma t, evidently a normal stress that's associated with the tangential or hoop direction, is forming as a result of the pressure that's acting on the cylinder, and those stresses will help equilibrate this free body diagram. So if I now go ahead and have a look at the sum of the forces along the y direction, and that direction is going to be positive for y, and so I would obtain, so first of all, sigma t is already in the positive y direction. It acts on two areas of the same size. So the length is L and the thickness is T. Now notice immediately that what I am doing here is I'm assuming that this value of sigma t across the thickness, across that direction, so in other words, the value of T from the inner point to this outer point is not changing at every point, and also along this longitudinal direction, it's not changing. Okay? In particular, the very fact that I'm omitting any possible variation along the radial direction, going from inner to the outside direction, indicates a strong assumption on sigma t. And that assumption, namely that it's uniform, is motivated by the thin wall assumption. All right. So the thin walled assumption allows me to assume it's uniform, so the net force is simply sigma 2t times 2lt. Good. So now we can try to equilibrate that force in the y direction with what actually is induced or imposed on that free body diagram by the loading, which is due to the pressure. So that is in the negative direction. And now my question to you is, well, if I incorporate that correctly, then the outcome should be 0. So that is essentially equilibrium. But what should I be writing here before? Because if I don't write the right thing, then I cannot calculate the tangential stress correctly, right? Eventually, sigma t will be found from this equality. So what should go in there? Think about that for a second and make a proposal. So it's going to be probably pressure times a certain measure of the area. Now, to motivate that, notice that if you've thought about it, well, suppose I have a block, an inclined surface, and on that inclined surface I have pressure acting, and I am interested in finding the statically equivalent representation or the components of the force on that surface in the horizontal and vertical directions. Okay, so if this dimension is L and this is H and this is W, so imagine that the thickness direction is 1. So without saying, I'm going to assume that the thickness is 1. So when I calculate, for instance, the force in this direction, it's going to be P times L and times thickness, which is 1. That's the force along that direction. What is the force in that direction, or the component of that force? Now it's going to be PL times the appropriate component, and it has to do with that angle, but L times the cosine of that angle is actually H, so it's going to be PH in that direction, and in that direction it's going to be P times W. So the force due to the pressure in that direction has two components, which is associated with the same pressure multiplying the dimension that is projected into the corresponding direction. If I'm looking at that direction, projection of L, the mirror image or the shadow of L on that surface along that direction is H, shadow of that surface along that direction is of width w, so it's p times w. So the next question I'm going to ask is, suppose I had an inclined surface like this, and this is L, and this is L, and this is H, and that is H. And the question is, if I have a pressure acting on these surfaces, well, what is the net force along this direction? Okay. So if you think about that question for a few seconds, you'll eventually deduce that it's going to be P times L, not L times cosine of probably that angle over here, right? But that's equal to H, L times cosine of that angle. So ultimately it's the same argument. P times the shadow of the surface, its length on the vertical dimension along that direction. So it's P times H, but there is also another contribution coming from there. So it's going to be 2PH. 2H is the shadow of that surface along that direction. So it turns out that it doesn't matter what the surface looks like, as long as you have one point connected to another through an height 2h, let's say in this case, and if you have pressure acting on that surface, irrespective of that shape and irrespective of this length, therefore, the net force along that direction is always going to be 2ph. So therefore, the net force in that direction is going to be P times the projection of this area along that direction, which is simply this length. And that length is 2r. So it is 2r times the length multiplying the pressure. So 2L. And now there's the thickness is not 1 here. It was 1 here. There's a dimension L. So it's 2RL, which leads me to the result that sigma T is equal to PR over T. Good. All right. So that takes care of the normal stress along the tangential direction. So that's sigma t or sigma theta. So now there's going to be also a sigma r associated with the radial and a sigma x associated with the axial directions. And that's our next goal. So because this is a log example, I will cut it and continue immediately.